The lesson outcome for this video is, I can graph radical functions using a table. Okay, so some of this may seem similar because we have graphed before using a table, both in linear functions and in quadratic functions, but now we are working on radical functions. So first, let's talk about what a radical is. So a radical is another word for square root. It could also be a cube root or a fourth root or a fifth root, sixth root, whatever, any of these, but just so you know, we will only be focusing on square root functions in this unit. Technically, because it's a square root, there is a little 2 right here, but since it's the most basic of the roots, we do not need to put that 2 in it, so we can erase that there. So this is a radical, or in other words, a square root symbol. And so a square root function is a function that has a square root in it. So here is our basic form of square root functions. Y equals a times the square root of x minus h plus k. Now I'd like to point out that this should look very familiar to you, because what we just worked on recently in class is quadratic functions in vertex form. And I'll write that down right here for a second. Y equals a parentheses x minus h squared plus k. Do you notice that the only difference between this equation that we've already worked with and this equation that we are starting to work with today is that instead of a parentheses around x minus h and a squared, there's a square root around the x minus h. So they are very similar, and they will have very similar work to be done with them as well. So let's start with what we call the parent function for square roots. Y equals the square root of x. We're going to just fill in a little table here, and we're going to graph our points and see what a square root function looks like when it's graphed. Here's a hint: it will not look like a parabola, like a quadratic function. So to figure out what a radical function's graph looks like, we can fill in x values, we can fill in x values in our table and find the corresponding y value and plot our points, just like we've been doing in other types of functions. But what does it mean to have the square root of x? Well, let's remember that a square root always means what number times itself gives you the number inside the root. So if I gave you the number 16 inside the root, the square root of 16 is what number times itself gives us 16. The answer is 4. So that's what we're going to be doing here. So let's think about what numbers would be good values to put in for x. Well, usually a lot of times we'll start with the number 0. So let's go ahead and put a 0 in for x here. So the question is, y equals the square root of our x value, which is 0. What is the square root of 0? What number times itself equals 0? And the answer there is 0. Right? Okay, let's try another one. What if we put a 1 in for x? So now we have y equals the square root of 1. Well, what number times itself is 1? And the answer there is 1. 1 times 1 is 1. All right, so maybe you're thinking that the same number will always come out for y when you put the number in for x, because that's what's happened twice so far. But we get to 2, for example. What if we put a 2 in here? Y equals the square root of 2. Well, there is no whole number that when multiplied by itself gives us 2. If you were to type in the square root of 2 on your calculator, what you would get is y equals 1.414. And we can graph that. We can graph an x value of 2 and a y value of 1.414, but instead what we might want to do for these remaining values here is pick better x values. And a better number for x is a number that when we put it into a square root, we get a whole number output. In other words, what number can we square root and get a whole number answer? Well, we just did one right up here. 16 works. But how about, let's just think, what's a little higher than 2? 3. Is there a number when multiplied by itself gives us 3? No. How about 4? The answer there is yes. The square root of 4 gives us a whole number because 2 times 2 is 4. So y equals 2 when x is 4. So we're looking for perfect squares. What's our next smallest, or the x value that is a perfect square? Well, 5 is not, 6 is not, 7 is not, 8 is not, 9 is, because 9 is what? 3 times 3. So if we put a 9 in for x, the square root of 9 is 3. Anybody know the next one? Well, if you think about it for a minute, we got 3 here and we got 2 here. So what about if we got a y value 4? That is the square root of 16, which we already talked about right here, right? So the square root of 16 is 4. So when I put a 16 in for x, I get 4 as my output. So now I have some values to plot on my coordinate plane. 0, 0, let's start with that one. 1, 1. And again, I mentioned this is not going to look like a parabola, so I wonder what it looks like. 2. Okay, now we have 2, 1.414, so 2 and 1.414 would be right about there. 4, 2 is here. And 16, 4, 9, 3, pardon me, 9, 3 is right here. And our last data point, 16, 4, will be a little bit off the grid here. 16, 4 would probably be around, whoops, about here maybe. So, what does it look like? Well, this curve can be drawn like so. And what it actually looks like is half of a parabola on its side. So if you can imagine the other part of the parabola kind of curving this way, but it's not there because it's only half of a parabola on its side. Now what you might be wondering is, shouldn't it go this way as well? And that's an important thing we need to talk about right now. So let's take a look at, what if I picked a -1 value? Okay, so what about when x is -1, is there a value here that we would continue our graph this direction? Well, no, there's not. Let's talk about why not. Here's my function, y equals the square root of x, right? And that means we're going to put a -1 in for x, so we're going to get y equals the square root of -1. So the question is, what number times itself is -1? Well, the answer is that no number exists that when multiplied by itself gives us -1, because a negative number times a negative number is positive, and a positive number times a positive number is positive. So there's no way I could multiply a number times itself and get a negative value, which means that there is no point at -1 for an x value. This graph starts and does not continue past this location right here. So this is the total and complete curve for this radical function. All right, let's try another example using a square root function. Y equals 3 times the square root of x minus 2. This time I've given you some x values to use, and I want you to see what happens with this first value of 0. So if I put a 0 in for x, I get y equals 3 times the square root of 0 minus 2. Well, 0 minus 2 is -2. What did I talk about on the previous screen here? Right? The square root of a negative does not exist in the real number system. And we talked about that when we were doing the quadratic formula earlier in the trimester, that there is no real solution if there's a square root with a negative under it. So, since the square root of -2 does not exist, there is no point with a 0x coordinate. Let's try 2. Y equals 3 times the square root of, we'll put a 2 in for x, minus 2. Again, I'm just using this right here, copying everything down and putting a value in for x. So y equals 3 times the square root of 2 minus 2, which is 0. Well, 3 times the square root of 0, well, the square root of 0 is 0. So we have 3 times 0, which is 0. So y equals 0 when x is 2. We'll go ahead and fill in the rest of these. Y equals 3 times the square root of, putting a 3 in for x, 3 minus 2. So y equals 3 times the square root of 3 minus 1, which is 1. And the square root of 1 is 1. So 3 times 1 is our answer here, 3. We'll go ahead and put 6 in. 3 times the square root of 6 minus 2 is 4. The square root of 4 is 2, so we have 3 times 2. And 3 times 2 is 6. Our last one, we're going to put 11 in for x. 11 minus 2 is 9, so we have the square root of 9. And we have 3 times the square root of 9, which is 3. And 3 times 3 is 9. Plotting these points, we have 2, 0, which is right on the x-axis. 3, 3, which is right about here. 6, 6, which is here. And 11, 9, which is right about here. And again, a little bit off of our screen. But notice, this is still a curve that looks like half of a parabola on its side. Notice we don't have any value at 0. We found out that was going to give us a negative. If I had put a 1 in, a 1 minus 2 would also give us a negative under the root. So this is our graph. Okay, let's try one more example. So this time we're going to put in these x values for our radical function. Y equals negative 2 times the square root of, I'm going to put a 1 in for x, plus 3, and then minus 4. Now you got to be careful. Notice the root ends here after the 3. It does not go over the negative 4, so don't put that over. So when we simplify this, and again, most of us might use our calculators here, but we need to be careful to put parentheses then around this. But if we calculate this by hand, we get negative 2 times the square root of 1 plus 3, which is 4, minus 4. And y equals negative 2. The square root of 4 is 2, so negative 2 times 2 minus 4. And following the order of operations, we need to multiply next. So negative 2 times 4 is negative 4 minus 4. Well, negative 4 minus 4 is negative 8. So our y value is negative 8 right here. Now what I'd like you to do is pause the video and either show these by hand or go ahead and put these values in for x with your calculator and find the y values, and then check back to see that you have the right y values before you graph. Again, one thing that you have to be very careful of if you're putting this in your calculator is that you put parentheses around what is under the root, but not around this. It shouldn't go there. All right, give it a try. Okay, so this is what your table should look like. I didn't have space to show my work for this last value of x, but I do have all of the answers in for y. And again, we can plot our points. We have 1, negative 8, so positive 1, negative 8 is down here. And then we have 6, negative 10. And we have 13, negative 12. Again, this will be a little bit off our screen. 13, or coordinate plane. 13, negative 12 would be about down here. And now we have negative 2, negative 6. I'm just wondering, did any of you think that negative 2 could not be put in for x? Because it could, because negative 2 plus 3 gives us 1, so it's still a positive number under the root. So negative 2, negative 6 is here. And then lastly, negative 3, negative 4. Negative 3, negative 4 will be right here. And the curve looks like this. And we're going to talk a lot more in class about how this point is found by using our equation. And if you want to think a little bit about that, it might help before we get to class.